Hello everyone. Today we will continue discussing our topics in DC machines. In the previous sessions, we discussed together the different types of DC machines and the different types of speed control, and we solved one example regarding the Ward-Leonard technique speed control. So today we are going to continue discussing some solved examples in the same topic. So let's start together with this solved example. In this example here, guys, a 250 shunt motor. So 250 is referring to the terminal voltage of the motor. Shunt motor is the type of the connection. So shunt means the field winding and armature windings are connected in parallel. So this motor has an armature resistance of 0.25 ohms and the field resistance of 125 ohms. So as you can see here, this is the motor connection. This is the armature windings. And here we have the field winding. And again, guys, the winding can be represented by RL or R as you can see here. But in steady state model, we do not consider the inductance in our model. Just in transient analysis, we consider the inductance of the windings. So the motor absorbs 25 kilowatt. So this is the input power that is absorbed from the DC supply. For sure, guys, DC motor will be supplied from DC source. So we don't have apparent power here. We have just active power. So this is going to be the amount of input power. But this is at which loading condition? He mentioned that this amount of power is absorbed at rated loading condition. So this is at rated value or nominal value. However, at no load, if the motor has zero mechanical output, so at no load, the motor current is 12 amperes. So this is the no load condition. So I can say now I at no load equals 12 amperes. And at full load, the total absorbed power is 25 kilowatts. Also, he mentioned that the motor current is 12 ampere and the motor current at no load is 12 ampere and the speed is 1000 RPM. So 1000 RPM is the no load speed, which is in node or in at node. So if we draw the torque speed curve, if this is the RPM in rotor and this is torque, so this would be the value of N no load. What do we need here in this question? So first thing is draw the equivalent circuit. So equivalent circuit, drawing the equivalent circuit can be like that, guys. Just refer to having the armature winding in parallel with the field winding. It's not a condition to have the inductance in 90 degrees like that, but 90 degrees here with the inductance means you have the angle between field and armature circuit in terms of the configuration of the windings. Okay, it has to be 90 degrees. And I don't care about that in the schematic, so simply you can say this is the schematic. You have the armature resistance, and you have here the induced voltage EMF of the motor. So this represents the armature the armature branch, and then we have here the field branch. So this is R field, this is RA, and this is here the induced voltage EA. And by the end, these are the terminals. So this is V terminal here, and this is I input to the motor. This is here I field, and this is the armature current. So this is the schematic. So this is the textbook drawings, and this is, you can make it easier like that if you don't need to make the inductance in parallel or 90 degrees like that, and the resistance in parallel like that. Okay, so this is part A. Part B, calculate the motor constant. So the motor constant is the factor Ka. So you remember, guys, the factor Ka depends on the winding technique and number of turns and some parameters of the motor windings, but we don't have these parameters right here. So this means we will get the value of the motor constant from the other relations or from the operating conditions. So we have now two operating conditions, rated and no load, but we don't know a lot of data for the rated, just the amount of power at rated. And for no load, we know the current and speed. So how can we calculate that? So let's start firstly doing the analysis. So at no load, we have 12 ampere and we have 1000 RPM. At full load, we have the 25 kilowatts. If you would like to get the field current, which is load independent, since you have 250 volt here, and this resistance is 125 ohms, so this is going to be constant all of the time. So IF is constant, and it should be 250 divided 125. So starting with the field current, so the field current is 250 divided 125, which is 2 amperes. If we would like now to get the armature current in no load condition, so we can say that the input current is 12 ampere, and we have 2 amperes going in the field current here. So the remaining current is going to be the armature current. So we can say at no load, armature current is 12 minus 2, which is 10 amperes. Now, since you have the armature current, you can calculate the armature volt. So the armature volt is VA minus IARA. So it's going to be 250 minus 10 times 0.25, which is 247.5 volt. Some cases, guys, if the data are not given for the no load, we can assume that the voltage across the resistance, armature resistance, is neglected. And we can say that the induced voltage is approximately equals the supply volt, the 250 volt. So this is acceptable if the data is not given in the problem. So since we have the data, we calculated the value of the induced volt. So we can say now the induced volt equals Ka phi times omega, and omega can be calculated from our no load speed. So we can say omega equals 2 pi times n divided 60. So we have n at no load, which is 1000 RPM. So we can calculate the angular speed, which is 104.72 radian per second. So this is omega at no load. So this is the no load speed in radian per second. Now, you know that the relation of the induced voltage that we calculate is nothing but Ka, the motor constant, times flux times omega. So since we have the value of EA, so this is the value of EA, and then we don't have flux. However, we can get the variable as a function of the field current. So we can calculate the variable of the motor constant dependent on the field current, not the flux. So this is another definition for the motor constant, guys. So we can say E equals Ka times IF times omega. So the IF is already calculated. So we have 2 ampere IF, we have omega. So we can get the motor constant as a function of the field current, not flux. So this is also acceptable, or one of the ways to calculate the motor constant. Especially if you are going to use this motor constant again to make some calculations in the same question. So this is our motor constant right now. Part C, we need to calculate the speed regulation and torque at full load condition. So we have the full data at no load, so we use the full data at no load to get the variable or the motor constant Ka. In order to continue calculations here in part C, we need to use the Ka. So what values are we requiring here? We need to get the motor speed and then speed regulation. It may be the first time to hear about the speed regulation, so we will see what is the speed regulation. And we need to calculate the torque. And definitely the loading condition has to be given, which is full load condition. So in case of full load, we know the value of power. So the power is given at full load. So we can use this power to know the input current since the supply voltage is given here. So we can say the armature current, the input current is power divide V. So for the full load condition, we can say now the total current equals power, which is 25k watts. So 25,000 divided 250 volt. So the total current is 100 ampere. We need to get the armature current, use the induced voltage relation. The armature current is going to be the total current minus the field current, which is constant, all of the machine operating points here, because the field is constant. We don't have variable resistance in series with the field winding, so the field current is constant. So in this case, guys, the armature current is going to be 98 ampere. Once we calculated the armature current, we can substitute now in our induced voltage relation. So EA equals V minus IARA. So 250 volt minus the calculated armature current, 98 ampere, times the armature resistance, 0.25. So we can get the amount of the induced voltage at full load condition. For sure, guys, this amount of induced volt in case of full load is going to be less than the amount of E at no load condition. If you go back, or no, back here, so this is the no load condition, induced volt, it's higher because the armature current is small in case of no load. So after getting the value of the induced volt, we can now calculate our motor speed. So we can say now omega equals E divided KIF. So the induced volt is 225.5, Ka is calculated in part B, and IF is 2 ampere. So substituting here, guys, you will get the value of omega. Again, the value of omega at loading condition has to be less than the omega at no load. So this is omega no load. So we expect the load, assume that this is the full load condition here. So this is the loading condition or full load. So the value of omega here has to be less than the no load speed. So this is our omega torque characteristic. So this is omega. We can get the RPM by multiplying these times 60 divided 2 pi. So N at full load is 907.06. So this is the speed at full load. Now we need to get the speed regulation. So speed regulation, guys, is like the same concept of the voltage regulation. No load volt minus full load volt divided full load volt. So here is the same. No load speed minus full load speed divided full load speed. Since in DC motor, the no load speed, or not only in DC motor, on all motors, no load speed is going to be higher than full load speed. So all of the time, the speed regulation is going to be positive value. So in volt regulation, we may have, especially in AC machines, we may have volt regulation in positive or in negative. It depends if the voltage of the no load or full load is leading or lagging power factor. So, or the machine operation is leading or lagging. Like if you remember in transformer cases, So most probably lead will have negative voltage regulation. So in this case, guys, the speed regulation compared to the volt regulation, all the time the speed regulation is going to be positive value because no load speed has to be higher than full load speed. So 1000 minus 907 divide 907, and don't forget to multiply times 100 in order to get it in percent. So the speed regulation is 10.24%. Now we need to calculate the full load torque. So the full load torque can be obtained either from power and speed or Ka times I, Ka phi times I. So let's get it from power. So we have Ea and Ia. So and again, guys, this is not the output power because you have some losses on the field winding. We consider these losses right here on the field winding. So the 25K is the input power, not the output power. So we cannot use it to get the torque. If it is output power, you can use it to get the torque. So torque is the developed power divided omega m. So the developed power is the induced volt times Ia. So this is induced volt we calculated at full load times the armature current at full load divide the motor speed in radian per second. So this is the amount of torque which is measured in Newton meters. So this is the full load torque. Another way you can use the, let's say here, this is another, I'm sure, let's see. Okay, so it's not solved by the other way. So we can say here another way, you can say it's equals to torque equals Ka times phi times Ia. Here in this question, instead of Ka phi, we use Kaif, the form of Kaif. So we can say torque equals, let's say this is prime for instance, so Kaif that we calculated times Ia. So this is going to be the value of Ka is 1.187 times If, which is 2 ampere, times the armature current, which is 98. Let's do these calculations outside and compare it with the value in the solved example. So 1.187 times 2 times 98. So this gives 232.652 Newton meter. If you compare these values, you will find very small calculation error, which is acceptable. So this is the amount of torque in this question. And by the way, the most probably, guys, the error in these calculations, as you can see, it's in hundredths. So this is just because of rounding some numbers on the calculators. Okay. So here, guys, in this example, the difference compared to the previous examples was the no load condition was given exactly. So we didn't say that at no load induced volt equals terminal volt. Why? Because we have the full data. Since the full data is given, so you can make exact solution. Okay, but if you don't have the full data, you don't have the current at no load, so the best way is to assume that the induced volt equals the line volt, because the voltage drop across the armature resistance can be neglected in this case. It's going to give very small error, and you can assume that and continue the solution based on this assumption. Okay. Let's solve another example. A DC motor develops a torque of 30 Newton meter. Determine the torque when the armature current is increased by 50% and the flux is reduced by 10%. So we have a certain DC motor, guys, and this DC motor provides a torque of 30 Newton meters. So this is the electrical torque that the motor provides at a certain operating condition. The question says, what would be the value of the torque if the current is increased by 50% compared to the first case, and the flux is reduced by 10% compared to the first case? So this is a matter of comparison here, guys. And the interesting in DC motor is the linear relation between torque and current. So we can relate the values. So we can say that torque is proportional to IF times IA. Because you know the relation is, the exact relation is torque equals constant times flux times IA. Or constant, let's say this is with prime, times IF times IA. So by the end, if you remove the equal and constant, we can say that torque is proportional to flux times IA or IF times IA. So simply from this relation, we can write down that T1 divided T2 equals IF1 times IA1 divided IF2 times IA2, since the relation is linear and both are directly proportional to torque. So we can make the comparison right now. Assume that the first case here, for instance, is 30 Newton meters. So T1 is 30 Newton meters. And this is the first case current. This is the first case current field under measure. And we don't know the numbers exactly, but we can make a relation. So he mentioned here that the current is increased by 50%. So current is increased by 50%. This means the armature current in the second case equals 1.5 times the armature current in the first case. And he mentioned also that the field current has been reduced by 10%. Take care, reduced by, not reduced to. Okay, so or increased by, not increased to. So increased to, it would be 150% if it is increased to. Okay, but reduced by or reduced to, this is sometimes tricky. So if I said reduced to 10%, so the new value is 10%. But reduced by 10%, so this means the new value is 90%. So phi in the second case, or flux in the second case, is 0.9 times flux in the first case. So phi M2 equals 0.9 phi M1. This is 1, not 2. So we can say now T2 divided T1 equals 0.9 times 1.5 divide 1, because flux will be removed, IA will be removed, and K is constant. So you can say this is equals 0.9 times 1.5. So this is T2 divided T1. So we can say now T2 equals 30 Newton meters times 0.9 times 1.5. So the new torque value is 40.5 Newton meters. So this is the new value of our torque that is needed here. So the purpose of this question, guys, is to allow you to practice the case of speed control if you have current control and field control at the same time. But to be honest with you, we do not do both of control techniques at the same time. So if you need to make field control, you don't need to make armature current control at the same time. You have to keep one of them constant. Okay? As we discussed these guys in the previous techniques, even with the Ward-Leonard technique, the armature current is controlled to be constant all of the time, and in a part of the time we control the volt, and another part of the time we control the flux. So this is the way how can we make control of machines. Okay, but this doesn't mean that we can use both. We can use both, but not at the same time. So at different steps, or make it in 2 steps, okay, until reaching to the required operating control speed or control torque. Let's go to another solved example here. "250-volt DC shunt motor has an armature resistance of 0.1 ohm and field resistance of 250 ohm. At the full load, its input power is 14 kilowatts at 250 volt, and the rotor speed is 1000 RPM. Calculate the speed regulation and neglect the armature reaction." Actually, if you compare this to the first example we solved, it's going to be very close, just numbers are a bit different. Okay, so what are different things we didn't consider in the first example? So let's see together what are the differences we have right here. So in the first example, we had a full data for the no load condition. If you go back to the first example here, in case of no load, we have the current value and the speed. So both were given at no load condition. Here in this example, we have the full load. At full load, the input power was 14 kilowatts, and we know the volts, so this is similar to what we had before. And the rotor speed is 1000 RPM. So we don't have the no load condition. We don't have the no load condition in this example. Calculate the speed. So how can we proceed? So let's start by the same way. The input current is going to be power divided volt. So the power at rated condition, the input power is 14 kilowatts. So 14,000 divided 250. So the input current is 56 ampere. Now, since the machine is shunt winding machine, so the field winding is 250 ohms. So we can say that the field current here is 250 volt divided 250 ohms. So we have 1 ampere field current. So the armature current is going to be the difference. IA equals line current minus field current. So this is going to be 55 ampere. Next step is to calculate the induced volt. So we can say EA equals V terminal minus IARA. So this would provide us with the value of the induced volt at full load condition. In order to continue, we need the value of KFI in order to calculate the speed. So we need to calculate the speed regulation. So speed regulation means you need the full load speed and the no load speed. You need to have both. So in order to get the full load and no load speed, you need the value of KFI. How can we get the value of KFI? So simply we can say that the KFI is E divided N. Here even we calculated divide N, not divide omega. You can calculate the KFI together, the flux multiplied time Ka, since you will not make any field control. So you can combine the KFI together, and you can play with the units. Instead of E divide omega, it could be E divide N. So instead of volt divide radian per second, it can be volt divide RPM. So we can say now, induced volt is 244.5 divide the value of N. So this is going to be 0.2445 volt per RPM. And if you use it again, you have to consider or respect the ratio, volt divide RPM, not radian per second. So the full load speed is given. We need to get the no load speed. So no load speed, we don't have the no load condition to calculate the no load speed here. However, we can say, assume that the no load speed equals V divided KFI. So this is the assumption that we mentioned before. Since we don't have the no load data, you can assume that the N at no load approximately equals VT divided KFI. So if you divide 250 divide 0.2445, so you would get 1022.5 RPM. Again, the no load speed has to be higher than the full load speed. So full load speed of 1000, no load speed of 1022.5. Since we have now both of speeds, we can do the calculation of the speed regulation. So N full load minus N no load minus N full load divide N full load, multiply times 100 in order to get it in percent. So this would be 2.249%. Okay, so this is the speed regulation of this motor. Another example here, guys, for the motor speed control using Ward-Leonard technique. So we have here a variable speed drive system uses a separately excited DC motor that is supplied from a variable volt. So we have variable volt supplying this motor, and take care the motor is separately excited, which means we have two sources, one source for the field and one source for the armature circuit. He mentioned here, guys, the torque and the power profiles are shown in the figure below. So this is the Ward-Leonard technique that we mentioned before. So for the Ward-Leonard technique, guys, we have voltage control and field control. The voltage control stage is going to be at constant torque operation, and the field control is going to be at power control operation or constant power operation in order to avoid overloading our machine. So in this case, guys, he mentioned here the drive speed is varied from 0 to 1500 RPM. So we have a range for the variable speed drive from 0 to 1500 RPM. And we will have a separate discussion, guys, for this expression, what the meaning of variable speed drive. Variable speed drive system. We will discuss a bit about this one in our lab. So we have a variable speed drive that provides a speed range from 0 to 1500 RPM. So the 1500 RPM is our base speed, which is the maximum speed we have in our design. This is coming by voltage control by varying the terminal volt from 0 to 500 volt. So by varying the volt in this range from 0 to 1500 to 500 volt, we have a variable speed range from 0 to 1500 RPM. And he mentioned here one important thing, which is with the field current maintained constant. So field current maintained constant means this is in the first stage. So here field constant. Part A in the questions, determine the motor armature current if the torque is held constant at 300 Newton meter up to the base speed. So this is the way, guys, we do this type of control. So this type of control depends on keeping the armature current constant. So we need to keep the current constant during the whole operation, but the first part of the operation is voltage control. The second part is going to be field control. Part B here, or part A here, is discussing the first part of the operation where the field current is constant. So the torque is 300 Newton meter up to the base speed, which is the maximum or the rated motor speed we have. So let's start calculating the armature current in this range and considering that the torque is 300 Newton meter. So the base speed in days is 1500. This 1500, guys, is the maximum speed we can obtain, which means this is going to be the no load speed. And this can happen, you know that this happen if we neglect the armature losses, the armature voltage drop. So we have V terminal equals almost EA. So we can say that K times phi equals V terminal divides the speed, since you know that the induced volt equals Ka phi times omega. Or you can say Ka prime phi times N. Okay, whatever the units. So here in this example, we use it in RPM, we multiply times omega, so we use it in radian per second. So Ka times phi is 500 volt divide 1500 RPM times 2 pi divide 60 to convert it to radian per second. So this is here 3.18 volt divide rad per second. Now we can calculate our current. So current equals torque divide Ka phi. So 300 Newton meter divide Ka phi. So this is the armature current. Part B, he said that the speed beyond the base speed is obtained by field weakening. So this is the second part or the second stage of the control. So the speed beyond the base speed or base speed, so from omega base to omega maximum, which is, as we discussed previously, most of the time is going to be twice of the motor speed. So he mentioned that he used field weakening in this part. So this is what we call, guys, for this range of control, we call it field weakening. So all of the time, having overspeed or overspeed the machine can be made by reducing the field. So we call it field weakening. Why weakening? Because it's beyond the rated speed. Why the armature voltage is held constant? We know that because in the second stage, the armature volt is going to be constant. No control, no voltage control anymore in the second stage. It's going to be only field control. So this means the armature voltage is going to be held constant at the value that produce the maximum speed, which is 1500 RPM. So this volt is going to be 500 volts. Now, determine the torque available at a speed of 3000 RPM. If we double the speed from 1500 to 3000 RPM, what would be the torque value compared to the previous, or what the new torque value? Because we know already the old torque value 300 RPM. And he mentioned if the armature current is held constant, and this is regular for this type of speed control. And he mentioned that neglect all losses. Neglect all losses because we consider that the armature resistance voltage drop is cancelled or neglected in our question. So in this part, guys, this is going to be the field control. So we are going to make field weakening until having the motor speed equals twice of the base speed. So what we can do is calculating the new KFI, and since we have constant current compared to part A, we can get the torque in part B, because you know that T equals Ka phi times Ia. So we don't have the torque in the second case. K phi is going to be changed, and armature current is going to be constant. So if we got the value of K phi in the second case, IA1 equals IA2, it's constant current. So we can get in this case the value of T once we get the value of K phi 2. So we need to get K phi 2 in case of twice of our speed, and consider that the voltage is still constant. So we can say N in the second case is 3000 RPM at the same voltage 500 volts. So we can get the value of K phi in the second case. So this is K phi 1, this is K phi 2. So 500 divide 3000 times 2 pi divide 60. So this is the amount of Ka phi at the second case. So this is still volt divide rad per second. 1.59 compared to 1.8, so it's almost half since the speed is twice at the same voltage magnitude. So we expect that the second value of torque, so T2 equals Ka phi 2 times the same armature current. So this is IA2, which is equals to IA1. So we can get the torque value, and it makes sense that the torque is going to be halved compared to the first value. Another way is to get it from power divided omega. So power is nothing but E times I. So EA times armature current, so armature volt times armature current, divide the same or the speed in the second case, so we can get the value of the torque. So neglecting losses, where did we neglect loss? We neglect loss here, guys, in this assumption. Since V equals E, this means the voltage drop across resistance is neglected, and since we neglected the resistance, this means we also neglected the copper loss of the machine. So this is the meaning of neglecting all losses in our machine. Okay. So this is the end of our material in DC motors, guys. So we didn't go more in deep in series motors, but we just understand that series motor is used in high starting torque applications. We are not going to focus on series motors in our class because, to be honest with you, we have other important materials for induction, for synchronous machine, and we have a lot of applications in industry related to these motors. So series motors are not used a lot like other new motors in industry. So we will focus on other or just the mentioned types of machine, the separately excited machine and the shunt machine in our class. Thank you so much, guys, and see you in the next class.